So that's sort of the end of any new material or any kind of stuff I want to present. Now I'm just going to hang out until 12:30 and answer any questions people may have. So,
I have a question on PLC 10.
PLC 10. Okay, hold on one second. Let me see if I can pull that up easily. Joe stuff, PLC physics 4A, PLC activities, conservation of energy. Is it a question on the first one or the second one?
The first one.
Okay, so that's Physlit problem 7.7. Let me, Physlit. Mechanics, chapter 7, problem, 3 balls thrown off the top. All right. Share screen. Okay, so this is the Physlit. So these are all launched at different velocities. You're given the X and Y components of each. So one, if you figure out the speed, they're all launched at the same speed. Okay, so what's your question from there?
So it wants us to use conservation of energy to find
the speed of the balls just before they hit the ground.
I don't get why we would use conservation of energy and not just like the equations that we have, like where you find break it up into components and find the time.
Oh, so you could do that. But what you're going to find is that you would have to do it 3 different times because each one of these is a completely different scenario in terms of projectile motion, right? They all have different launch angles. But when I'm using conservation of energy, it doesn't matter what angle it's launched at. So one, let's just, can I click inside here? So this is 9, does it start at 0? -3 to 9. So it looks like these are all, that's kind of weird. So here, the very bottom of this is at -3. The top is at +9. So the initial height for all of these is 12 meters. So let me actually stop this share and do this as a white screen. So the situation is you've got these balls being launched from a height of 12 meters, and they're either being launched, I forget the angles, but let's just say they're being launched like this. In all cases, the initial speed ends up being 10 meters per second, and I can define my y = 0 to be at the ground level. So one, if I define my system to be the ball and the earth, once these balls are launched, the only force on them is the force of gravity, which means that there are no external forces. So there are no external forces doing work. There is no spring. There is no friction or air resistance, so I don't need to worry about thermal energy. So my big equation would end up being, well, I'd have the work done by external forces plus the initial kinetic energy plus the initial gravitational potential energy equals my final kinetic plus my final gravitational potential plus any change in thermal energy. Well, there are no external forces doing work. My thermal energy doesn't change because there is no friction or air resistance. My final gravitational potential energy is 0 because I defined y = 0 to be the lowest point. So what I basically get is the initial kinetic energy plus the initial gravitational potential energy equals my final kinetic energy. And so I have 1/2 m. What's that?
Would you define the initial velocity for all of them as 10 meters per second?
It is because, keep in mind, they gave you the x and y components of the velocity. The speed is always the square root of vx² plus vy². So for going back, let me just stop this for a second because I can go back to this, share screen. So like in this case, the blue ball, 6 meters per second in the X direction, 8 meters per second in the Y direction. You figure out the speed, that's 10 meters per second. Same thing for the green ball, same thing for the red ball. They all have the exact.
Speed is the same for all of them?
Say that again?
So the initial launch speed is the same for all of them?
Correct. So that means they all start with the same initial kinetic energy. They all start with the same initial gravitational potential energy, which means they're all going to hit with the same kinetic energy. And so you could use conservation of energy to figure that out. So I get my initial kinetic energy 1/2 mv initial squared plus my initial gravitational potential energy mgy initial equals my final kinetic energy. So we have every single term except for this v final, so you can use conservation of energy to figure out the speed they're going to hit the ground at.
Does that mean that they would also all hit at the same time?
No, most definitely not at the same time.
Okay, I didn't.
Right, if I, does this actually shoot these? So it doesn't actually show you, but yeah, I mean, you could clearly see or even imagine if I launch something straight down, it's going to hit sooner than something launched straight up or launched horizontally. So they're most definitely not hitting at the same time, but they are hitting at the same speed.
Are we supposed to represent that mathematically?
So for part C, you actually are calculating the speed of each ball right before it hits the ground using conservation of energy.
What about part B?
Oh, so one, you could mathematically get the answer, and that's going to be the same answer to each one. So in essence, you're kind of doing C first, but you could mathematically justify B by saying they all, let me stop this one again, start the other one. That's not it, sorry, stop share. So the way I would represent it mathematically is really just this, by saying they all start with the same kinetic energy. They all start with the same gravitational potential energy, which means they're going to all end with the same final kinetic energy, which must mean they all have the exact same speed. And then part C is where you're actually solving for what that speed is. Chat. The red ball has a negative y component. Wouldn't that mean that it would be faster? So wasn't there a problem in class yesterday that said the angle doesn't matter when the ball is thrown off there? Can we compare that to this problem? The red ball, it would just hit the ground. Yes. So I did do a problem, and let me actually stop this share one more time. Open up this one, and I think that was example problem. Okay, so this was problem 1013, where basically it's similar. You had something launched from a 10-meter high building, and the initial launch speed was 80 meters per second at a 30-degree angle. And in essence, we had the same setup, is the initial kinetic energy plus the initial gravitational potential energy equals the final kinetic energy. And what I was showing people in this one is that nowhere in this problem does the angle come into play, because kinetic energy only depends upon speed, not velocity. So this problem, instead of 30 degrees, if you used 45 degrees or 60 degrees or 80 degrees, that would give you the same answer. Now, what I challenge people to do, if they wanted to, was as a way of reviewing this, you could do this problem from projectile motion. And I would have to analyze each one of these separately, because keep in mind, if I have the launch speed and the angle, I know my initial velocity in the x direction would be v naught times the cosine of theta, and my initial velocity in the y direction would be v naught sine theta. So even though I'm launching all of these at 80 meters per second, if I have a different angle, I'm going to end up with different initial velocities in the x and y directions, And then when they hit, they're going to hit with different x and y components of the velocity. But speed is always vx squared plus vy squared. And every one of these examples, it doesn't matter what the launch angle is, you'll always end up it hitting the ground at the same speed. It'll hit at different times. It'll have different x and y components of the velocity, but it's always going to hit at the same speed if they're launched from the same angle, launched from the same height at the same speed. So again, I have a ball at a certain height, and I throw that ball horizontally. I can use conservation of energy to figure out how fast it's going to be going when it hits. If instead I throw it at a different angle, it's going to travel a different path. It's going to hit at a different spot. It's going to hit at a different time. But as long as they start at the same speed, at the same height, conservation of energy says they're going to hit at the same speed. Booyah. All right, that is.
I have a question.
Okay, quick question.
Should be quick. The whole equation that we're using for the energy, is that that's basically what the energy bar diagram is, right?
So yeah, so the energy bar diagram, you have one conceptual question on it. I'm not going to ask you any quiz questions or things like that, but it's just a way of, yeah. So
that's how I learned it last year in Physics 11. So
I like that. I like that. It's just one of those ones where, yeah, I had to sort of focus. So like in this particular one, if I were drawing an energy diagram, what I would say is, here's my initial energy. Here's my final. So initially, it's got some gravitational potential energy, and it's got some kinetic energy. I don't know the exact values. That's probably not equal. But at the end, right before it hits the ground, all of the energy is now final kinetic energy. So it's basically just like a way of almost like balancing your checkbook. However much energy I start with has to be the total amount of energy I end with, but it can be in different accounts. So here, the total energy it starts with is the sum of the gravitational potential energy plus the kinetic. So if these had values, let's say these were 5 joules and somehow they were both the same, and that means the total energy has to always be 10 joules. So when I go and do a final energy bar chart, all the forms of energy have to add up to whatever the initial energy was.
Cool, thank you. That's great. That's perfect.
Perfect. Yeah, and you know, I still think energy bar charts are super useful, but you know, in this new paradigm, I have to sort of decide what's the most important.
Cool.
All right.
So I have a quick comment question. I was looking at my homework chapter 8.
Who's that? Is that Jules? Or Sharon?
It is Jules. Hey,
Sharon.
and I noticed one of the questions I got a 0 on, which maybe I got a 0, but it says grade pending. And I just wanted to make sure everything was graded. It was like enter the answer yourself, type it up. And I want to make sure if I got it wrong, I need to study it. And if it hasn't been graded yet, then I'd love
which homework was this?
Celebration. Chapter 8.
Chapter 8. So I'm sorry. I've been
submitted with grade pending.
3 hours.
No biggie. Oh, it just says submitted with grade pending. And I just wanted to make sure it was graded before the celebration so I can double check everything I know.
Okay. I will look into that and just sort of make sure that, so as long as, just so you know, also, you know, in terms of the grading of the homework, it grades you on each individual problem. Just like before when we had classes on campus, I'm just grading on completeness. And so as long as you attempt every problem, you'll get 10 out of 10. And just to remind you also, the homework problems are the same ones that I've assigned before. So I have the solutions posted to all of those. It's just in Mastering Physics, it uses slightly different input variables. So the final answer may not be the same, but all of the steps of all of the problems should be the same.
But this one is like it's a like we had to type up an answer. It wasn't the multiple choice one. It said that the teacher would go in and read it and then hand grade each one.
Oh,
so
yeah.
I just wanted to make sure you were able to do that.
So no,
it's just, I know it's graded homework, so I was just curious if you'd graded it yet. Or if
those ones I'm not going to hand grade. So pretty much I'm just checking that people have submitted some answers for the homework, in which case I'm going to give everyone 10 out of 10 if you tried most of it. So
Okay,
the
got it.
answer
So
is-
it's not the grade that the Pearson is giving us. You're going to
No.
kind of just look and say, hey, you did it. Here's a 10.
Yeah, and you know, after the second celebration, I'll give out everybody's grades again so that people have a more concrete idea of where they stand. The quiz grades are fine. Like the quiz grades that you get from Mastering Physics are correct. But the homework grades, don't worry about those.
Okay. Okay, cool, cool. I just wanted to check in. Thank you.
Yep, you are welcome. All right, that is it. I'm out of here. Have a wonderful Tuesday. I'll see you guys on, well, tomorrow I'm going to make up another video on a video on chapter 11, but labs are already posted for tomorrow. Should be a fun lab. That's it. Happy Tuesday.